Spontaneity in chemical reactions. Not all of thermodynamics is concerned simply with energetics. It's also concerned with the likelihood that a reaction is going to occur under specified conditions. A spontaneous reaction is one which occurs to form product, while the non-spontaneous reaction is one that does not occur to form product. Spontaneity depends on the relative stability of the products and the reactants. If the products are more stable than the reactants, the reaction will tend to be spontaneous and move forward towards product. If the reactants are more stable than the products, the reaction will tend to be non-spontaneous and will favor the reactants. Some reactions are always spontaneous, while other reactions are never spontaneous. Most reactions, however, depend upon specific conditions. When we're looking at spontaneity, we never include the effects of an outside force like a catalyst on the reaction. What a catalyst will serve to do is to speed up a reaction, but we're not concerned with how it affects spontaneity because that is independent of this kind of process. If I reverse a reaction, generally its spontaneity will reverse. So if the forward reaction is spontaneous, the reverse reaction will generally be non-spontaneous, and vice versa. You can force spontaneity by altering the conditions under which the reaction is run. For example, if a reaction that causes the expansion of a gas is spontaneous, then normally the compression of the gas would be non-spontaneous. However, that process can be achieved under some conditions. For instance, if I were to increase pressure to a high pressure, that can often cause the process that would be originally non-spontaneous to become spontaneous. The only thing we are concerned with spontaneity is the likelihood that a reaction will form product. This is not related at all to the rate or the speed of the reaction. Now, aspects of spontaneity, most or many reactions that are spontaneous are exothermic. Not all reactions which are spontaneous are exothermic, and not all exothermic reactions are spontaneous. For example, freezing water is exothermic. In order for water to freeze, it has to slow down, which means it has to give off energy. Ice will freeze spontaneously below 0 degrees Celsius. However, above 0 degrees Celsius, ice will not freeze. It will just stay as water. Ice will melt spontaneously above 0 degrees Celsius. Melting is an endothermic process by which the ice has to absorb enough energy to speed up and escape the attractive force that holds it as a solid. Now, spontaneity will always favor the release of energy, but it does not always occur when heat energy is released. Generally, an exothermic process will favor spontaneity, and an endothermic process will disfavor spontaneity. While exothermic and endothermic processes are important in considering spontaneity, there is a second factor that is also important, and that is the dispersal of energy and matter in the system. We can look at a system and consider the number of possible energetically equivalent configurations it can have. The higher the number of possible energetically equivalent configurations, the more spontaneous a process will tend to be. This is what we would call an increase in disorder. Overall, a spontaneous reaction is favored by a release in energy, whether that energy comes from an increase in heat transfer, an exothermic process, or whether it comes from a release or dispersal of matter and energy through a dispersal process. Dispersal of matter and energy spreads energy over many particles, not over a few particles. Generally speaking, a sample will not sit with a small number of particles with high energy and the rest of the particles with low energy. They will reach what we call thermal equilibrium, where the energy is more or less evenly distributed throughout all the particles. The larger the number of molecules and the higher the total energy, the more likely it is to be distributed over a large number of particles. Therefore, the less likely it will be distributed over a few, because there are more particles to receive the energy and more energy to be distributed. This causes what we call a Maxwellian distribution of speeds, where if we look at the percentage of particles that are in a particular configuration and the overall speed or temperature, the system forms something of a bell curve centered around the average kinetic energy or the average temperature of the system. Now, matter will also disperse as well as energy, and this occurs through a process called diffusion. If I had two containers connected together by a stopcock, where one was full and the other was completely vacuumed empty so that there was nothing in it. If I release the stopcock, if say there was a gas in the full container, it would move into the empty container and until we reached a point at which both containers had an equal amount of substance. If I have two containers, or two possibilities, every particle in the container has a 1/2 probability of occupying one of the two containers. It can be in the one or it can be in the other. It can't be in neither, so it's either in one or the other. The probability of all particles being in one container is the product of the probability of each occupying that container. So if there are two particles, each particle has a 1/2 probability. 1/2 times 1/2 is 1/2 squared, or 1/4 probability of both of the particles being in the same container. In this case, we're looking at the difference between the left-hand side, where they're both in one container, which has a 1/4 probability, or the right-hand side, where they're both in separate containers, which has a 3/4 probability. If I have a mole of particles, then the probability is 1/2 to the n power, where n is Avogadro's number, or 6.022 times 10 to the 23rd. This is an extremely small probability that all the particles will be in one container. Expansion into a large volume distributes more than expansion to a small volume. Matter and energy both will tend to disperse. This means that there will be probability of something condensing when we're expanding to a large volume is very, very small. Everything has a tendency to move towards a dispersal of matter or energy. This is because by dispersing, we reach a higher count of possible configurations. Now, a spontaneous reaction will then be one where matter is more dispersed or disordered. It's also be one where energy is more dispersed or disordered. So overall, the energy and matter in the system being more disordered or with a higher number of possible energetically equivalent configurations will tend to be a more spontaneous reaction.